At the start of its second week, the human embryo exists as a flat, two-layered structure called the bilaminar disc. It is composed of an upper layer, the epiblast, and a lower layer, the hypoblast. The central objective of this developmental phase is the initiation of gastrulation. Gastrulation coordinates a highly choreographed spatial migration where cells move to predetermined physical coordinates. This migration transforms the two-dimensional sheet into a three-layered structure comprising the ectoderm, mesoderm, and endoderm. These three germ layers provide the absolute structural blueprint for all future human anatomy. To build a complex 3D organism from a flat sheet, the embryo establishes a physical routing system to dictate the final destination of every cell. From a top-down dorsal view, the epiblast layer sits within a transparent region called the area pellucida. A dark, narrow, triangular thickening begins to form precisely at the caudal midline. This structure at the caudal end is the primitive streak. The streak appears dark because epiblast cells are rapidly thickening, converging, and crowding together along the midline of the disc. This streak elongates strictly from the posterior caudal end toward the anterior cranial end. The mature anatomy of the streak consists of a central depression, the primitive groove, flanked on both sides by raised primitive ridges. At the cranial boundary of the streak sits Henson's node, also known as the primitive node, which is a dense cluster of cells. Within Henson's node lies the primitive pit, a small depression that connects backward into the main primitive groove. The formation of the primitive streak and node establishes the embryo's first geometrical parameters, locking in the left-right midline and the cranial-caudal axis. A transverse cross-section through the middle of the primitive streak reveals the mechanics of cellular movement. Epiblast cells slide horizontally toward the center and drop into the space below. This process of migrating to the midline and diving through the streak is defined as ingression. To ingress, cells lose their rigid epithelial shape and become mobile, free-floating mesenchymal cells. Mesenchymal cells are characterized by their ability to migrate through the extracellular matrix independently. The first wave of ingressing epiblast cells dives through the middle space until they reach the bottom layer. These cells physically displace the original hypoblast cells, pushing them out toward the external margins. This new bottom layer, derived from the epiblast, is the endoderm. Through the mechanical force of ingression, the epiblast replaces the original foundation with a purpose-built internal layer. A second wave of ingressing epiblast cells follows, but these cells stop and spread in the empty space between the top and bottom layers. This intermediate layer is the mesoderm. The specific subtype of each migrating cell is determined by its exact point of entry along the primitive streak. Cells entering through Henson's node become axial mesoderm, migrating straight forward along the midline to form the notochord. The notochord is a rod-like structure that serves as the primary longitudinal skeletal element of the early embryo. Cells entering the cranial third of the streak become periaxial mesoderm, distributing on both sides of the axial midline. Cells entering through the caudal two-thirds become lateral mesoderm, migrating in a wide lateral and anterior direction. This continuous flow fills the intermediate space of the embryonic disc. The primitive streak functions as a spatial routing system, translating two-dimensional entry coordinates into three-dimensional anatomical destinies. Some epiblast cells remain on the surface and never migrate toward the streak. This remaining outer layer becomes the ectoderm. Mesoderm occupies most of the space between the ectoderm and endoderm, with the exception of two distinct zones where it is blocked. The cranial exclusion zone is the buccopharyngeal membrane. The caudal exclusion zone is the cloacal membrane. In these two locations, the outer ectoderm and inner endoderm are fused together, preventing any mesoderm from separating them. These fused zones establish the definitive entry and exit points of the future digestive tract. The embryo has transitioned from a two-layered state to a definitive three-layered structure. The epiblast is the sole source for all three definitive layers. The final architecture places the ectoderm on the exterior, the patterned mesoderm in the middle, and the endoderm on the interior. The embryo now exists as a spatially organized grid with established head-to-tail, left-to-right, and inside-to-outside coordinates. Gastrulation provides the spatial coordinates necessary for the onset of organogenesis, the phase where these layers begin to differentiate into functioning organs.